If you don't have any question, then I would proceed. Okay. Now, let's go back to the initial setting right here. What I was saying is, hey, we have a single reactant called A, and it's going to make product B. And then we investigated three different types of orders: zero order, first order, and second order. Okay. And we talked about integrated rate law. And now I would like you to train your ears to know there are two different things. What we were just talking, there are three equations, right? Those are integrated rate law. And what I am about to show you what I'm about to show you, it's called rate law. Now, it's a little bit confusing in the very beginning because this is brand new, but the more you see them, it's going to get better. Okay? So, how do you write a rate law? Not the integrated one. How do you write a rate law? The way you write the rate law, it's always going to have this kind of formatting. Okay? It's going to be K times the concentration of the reactant. Now, if there are more than one reactant, then you will have more to multiply. But for this case, we have only a single reactant. So we'd say, all right, just A. But A to the what power? That is the question. A to the what power? Well, that's why we have these orders. They're the powers. Okay? Well, what is anything raised to the zero power? 1. So that means if it is zero order, the rate is simply K. Okay? The rate is simply K. Cool? Cool. That's the rate law. So that's a rates law if you have a single reactant with zero order. This is a first order. This is a second order. Now, something that you need to feel comfortable is that we will keep the word rate and also the letter K. We are not going to put in numbers right here, right now. These circled ones are the finished product, the finished outcome of writing a rate law. Cool? All right. Now, if you're good, let's go ahead and practice something. But before we do, I also want you to remember this quote. Rate law can only be determined experimentally. That's why you will see some questions on, if you go to page 11, let's see, yeah, page 11, there's a little table right here. Let's see if you can match a table. Okay, with a little bromate ion plus 5 bromide and 6 hydrogen ion. Okay, so now for beginners, you might feel so overwhelmed with this gigantic table. And now we say, hey, go ahead, write a rate law. So let me help you break this down. What are we doing here? What are we doing here? We are simply doing this. Rate, it's equal to K times BrO3 minus raised to a power, which we will find out in a moment. Br minus raised to another power, which we'll find out in a moment. and then times H plus concentration, and it would be raised to n to the power that we will find out in a moment. So we're not done yet. We still have to fill in the exponents, but that's like the backbone of the rate law. It would only involve reactants. Okay? The rate is only impacted by the reactants. Are we good so far? Yes? Well, how are we supposed to find the exponents? Now, first, I will show an easy way. We will go ahead and look at mixture A and mixture B. And sometimes they would call it experiment 1, 2, 3. Like if you look at the table down below, can you see experiment on the left column? Okay. We're not talking about the same thing. But what we're trying to do is this. Let's just say I want to find out this exponent. I want to find out if the concentration of bromate ion changes, what will happen to the rate? Now, if I want to make that observation, it would be really helpful that these two concentrations are not changing. So, well, very luckily, for mixture A and mixture B, bromide concentration and hydrogen ion concentration, they are not changing. So we say, hey, look at this. See what's the change right there? This is a double. The concentration doubles. What about the rate? Also times 2. So it's times 2 here. It's also times 2 over there. Then we say, oh, which order is it? Not second. It's first. Okay? First order is the directly related. So if it doubles, if the concentration doubles, the rate doubles. If the concentration drops by 1/2, then the rate would also drop by 1/2. If the concentration triples, like times 3, then the rate would also multiply by 3. So that is our first exponent. We say, oh, hey, it is first order in respect to bromate. First order in respect to bromate. What about bromide? Well, which two mixtures would be great to tell the order of bromide ion? B and C, because the concentration of bromate and hydrogen ions are both unchanged. Then you can observe like, hey, this one doubles. And this one also doubles. Therefore, first order. Also first order. Are we okay so far? Okay. All right. So to find out the order for a hydrogen ion, we shall focus on C and D because, well, the other two reactants have the same concentration. This one doubles, but this one, the rate, quadruples, squared. So then we say, oh, so the reaction is second order in respect to hydrogen ion. And that is our Rate's law. Okay? That is our Rate's law. So far, so good? All right. Now, then there's always one question. What is the value of K and what is the unit of K? Now, there would always be a question about unit of K. So now, let me backtrack a little bit. Let's come back to here. Let's come back here. Now, rate, it's always going to have a unit of molarity over some unit of time. So let's just say seconds. Or let's use minutes. Minutes. I think minutes would be a more conventional. Okay, so some kind of time unit. So now the unit of K, it's not always the same. But you know what's the same? It's an equation. So if the left must have a unit of molarity per minute, well, guess what? The right hand side of the equation must have an overall unit of molarity per minute. So in this case, if it is zero order, well, K shall assume the unit of molarity per minute. Now, sometimes you would also see this alternate expression of molarity per minute. It's just breaking down the molarity to moles per liter. All right, now, let's see how good your math is. What about the K for first order reaction? What unit should it be? Again, the rate would always have molarity per minute. What is the unit of K so that both sides are equal? Now, don't forget that we are multiplying by the concentration of A, which is in molarity. So what should be the unit of K in this case? Huh? No. How do you make both sides equal? What will you insert into this orange parentheses? Minutes in the numerator or denominator? Denominator. That's the unit of K. Okay. So the way you think about the unit of K, you don't have to memorize it. You just have to figure out the simple math right here. It's an equation. They have to match up. So now, with this understanding, let's keep pushing. What about the unit of K? For a second order reaction. If you can name whatever you need to name in order to keep this equation valid, what must be the unit inside the orange parentheses? It's ugly, but hey, it is what it is. It is what it is. Don't put too much emotion into this. Okay? It won't stay with us for too long. Good. All right. So now the next question of this problem is, what is the value of K? So what you would do is to pick any set of reaction. Any, because the K shall be the same for all four trials. So I can say, well, let's just go use the first row. So we have this basically 0.03, 0.025, 0.005. So what is the K value? Ten divided by 0.005 divided by 0.025 divided by 0.03 squared. It's going to be gigantic. It is 8.89 times 10 to the 1, 2, 3, 4, 5, 6, 7. Okay. What's the unit? What's the unit for this K value? Molarity per unit time. Oh, they don't have the, let's just call that minute. Okay. Right. So what is the unit of K? Same idea. How do you create a unit for K so that it is a valid equality? 1 over what? 1 over m cubed times minute. Okay? Because overall right here, it's m to the 4th power. You just need one single m right here. So that's why you need to divide 3 of the m's away. That's it. Okay? All right, it's new, it's a little bit complicated, but it's not too overwhelming.